Hey guys, we're continuing chapter 15, which talks about equilibrium. And I want to talk about the value of the equilibrium constant and what it means. So remember that it is the ratio of products to reactants raised to the power of their coefficients, whether it's Kp or Kc. And so it kind of gives us insight as to, at equilibrium, do you have mostly products? Do you have mostly reactants? Do you have, about equal amounts? And so it tells us, what are the concentrations basically, or the ratio of the concentrations at equilibrium of products to reactants. So if your K value is extremely large, we said that if it's larger than 1, that means you have more products than reactants, right? But what if it's extremely large, like, something times 10 to the third or fourth or 10th or something like that? What does that mean? Well, that means that basically pretty much your reactants have turned into products. So pretty much at equilibrium, you mostly have products with very, very, very minimal reactants. It's negligible. So if your K is extremely large, like, more than thousands, then you can basically say, well, pretty much all of it is products, negligible amount of reactants. And so you can basically use stoichiometry to do your calculations. No need for ice charts anymore, right? Because if all of the reactants have turned into products, then we would use stoichiometry. So if your K value is very, very large, again, 10 to the fourth or 10 to the fifth or 10 to the eighth, then you can use stoichiometry. There was a problem recently on an AP exam where K was like something times 10 to the ninth or something like that. And, all students used ice charts and did really complicated math and they got it wrong. And students who used stoichiometry got it right because they understood what the value of K means. Now, what if it's the other extreme? What if K is extremely small? Very, very small. And when we say very small, we're talking about in relation to the initial reactant concentration. So if your initial reactant concentration is 1 molar and your K is something times 10 to the negative eighth, for example, it's negligible, right? What that means is that pretty much most of it remains as a reactant. Very, 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 very little product has formed. And so when that happens, you can make your math a little bit easier by ignoring the X when you subtract it from the initial reactant concentration. What does that mean? So for example, if your K expression is like X times X over 1.5 minus X, right? So let's say your initial concentration of, these are of course your products, right? The reactant, let's say, was 1.5 molar and your K is, again, something times 10 to the negative eighth, for example. Well, X is going to be super, super small, that when you subtract it from 1.5 is going to basically equal to 1.5. So if your K is super, super tiny compared to your initial concentration, so I'd say like 10 to the third difference between them, or 10 to the fourth difference between them, then you can just ignore the minus X here and make your math a little bit easier. If it's pretty easy for you to plug it into your calculator, that's fine. You can keep it as minus X, of course, but if you want your math to be a little bit easier, you could do that if your K is super small. So these are just helpful tips to understand the meaning of K. Now, we can, if we know K or Q for a reaction, we can actually know K or Q for a similar reaction. So we can rearrange K or Q a little bit to get the value for a similar reaction. So for example, if you have a reversible reaction, K for the reverse reaction is going to be 1 over K for the forward reaction. Basically, whatever you do to the reaction, you do to the power of K. So if you flipped it, like multiplied it by -1, the reaction, then you raise K to the -1, which means it's 1 over it. So K for a reverse reaction is 1 over K for the forward reaction. So what would be the equilibrium expression for the forward and the reverse reaction for the decomposition of water here? So K forward, if you were to write the K expression for the forward reactions, would be products over reactants. So concentration of H2 squared times concentration of O2 over the concentration of the H2O squared. Now let's look at the reverse. So these are now my reactants and these are my products, right? So products, which would be this, so H2O concentration squared over the reactants are now these, concentration of H2 squared times the concentration of the O2. So you would see from here, from my two expressions, that K forward and K reverse are related, then the reciprocals of each other. So if I wanted the K reverse, I would do 1 over this, which would be this right here. Okay, what if you have changing coefficients? So let's write the K expression for this reaction. So K is going to be the concentration of the SO3 over the concentration of the O2 to the 3/2. Now let's look at this reaction. Well, I doubled it, right? This reaction is double of this reaction. Well, let's write the K expression for this. It would be concentration of SO3 squared over the concentration of the O2 to the 3rd. So how do these K's relate to each other? So to go from this reaction to this reaction, I doubled it. To go from this K to this K, I squared it. So whatever you do to your reaction, you do to the power of K. So if I doubled my reaction, I raise my K to the 2nd power. I square it. If I triple my reaction, then I raise K to the 3rd power. If I multiply my reaction by -1, like I reverse it, flip it, then I would raise my K to the -1, and so on. Okay, what if I'm adding reactions? So if you add these reactions, so let's try to do that. I see SO2 here and SO2 here, they cancel. So S solid plus 1 and 1/2 would be 3/2 O2 gas yields SO3 gas. So when I add these two reactions, I get this overall reaction. So then what do I do to my K's? Well, remember, whatever it is you do to the reaction, you do to the powers of K. So when you add powers, that means you multiply the values, right? So K for this would be equal to, this is overall reaction, be K1 times K2. So 4.2 times 10 to the 52nd. Oh, wow, that's a big number. Times 2.6 times 10 to the 12th. So whatever that value is, that's a really big number. 1.1 times 10 to the 65th. So that's my K for the overall reaction. So if you're adding up reactions, you multiply the K's. Okay, so let's look at this here. Kp for the dissociation of N2O4 at 25 Celsius is 6.75. So K for this reaction is 6.75. I want to know what the Kp value is for this reaction. So how does this reaction relate to this reaction? Well, it's reverse, right? It's flipped. So K for this reaction would be equal to 1 over, this is the reverse, K forward, so 1 over 6.75, which is I had to grab my calculator here. It is 0.148. Okay, let's look at this one here. So I want to know Kp for this reaction. How does this reaction relate to this one right here? It looks like we halved it, right? And so we take our K and take it to the power of half, right? So it'd be 6.75 to the power of 1/2, or the square root, basically, which equals 2.60. So if you know K or Q for a reaction, you can find K or Q for the reverse, or for a reaction that's multiplied by a certain number, or for added reactions together.